Yeah, bob of mass m suspended from an ideal string of length L. Calculate the speed at the bottommost position such that the string just becomes horizontal. Okay, let's discuss some ideas. Rishi, how do you think you can solve this?
Sir, since the angle is 90 degrees, so
Mhm.
what I did was the formula which you gave in the last class, T theta is equal to mu square by L plus 3 mg cos theta is equal minus 2 mg.
See, that
So,
that is the formula for tension as a function of theta. It is mu square by L plus 3 mg cos theta minus 2 mg. Okay. Using this formula, what will you get? I mean, you can substitute theta 90 degrees in this. What does it give you?
sir, no, sir, I don't think. One second.
Use of any idea?
No, sir.
Okay. Okay. Can you tell me the law of conservation of mechanical energy, Yusuf? Like when is mechanical energy conserved? Okay, fine. Make sure you revise everything. What topic are they teaching you at school now?
I don't know, sir. I haven't gone past few days.
But before that, the last time you attended, what topic was going on?
I think work power.
Okay. Okay. Fine. Rishi, tell me what exactly were you asked to calculate?
Sir, the U at it needs for it to go horizontal.
The initial speed required for the string to just become horizontal at least. Okay. Now, as the bob moves up, what can you tell about the motion of the bob? Or what all can you describe about it? Or what happens to it as it ascends? Uh, can't you describe anything about the motion of the bob as it ascends? Does nothing change
Sir,
at all?
as the tension, it won't be any factor to it because of the 90 degrees thing. But the force acting on it will change, sir.
Okay. What about its speed?
Its speed also,
Does the speed increase, decrease, or remain same?
sir, it has to increase, I'm assuming. I'm not sure.
Like you think of that Hot Wheels track case itself. As the car ascends up the slope, what will happen to its speed?
Oh, sir, it slows down and the
Ah,
car comes.
then when anything goes up, speed has to decrease because of gravity.
Yeah,
Gravity is acting in the downward direction. Tension here does not do any work. We had discussed that many times. And so if an object ascends, gravity does negative work. So it will make it slow down. Okay, we want the string to just become horizontal. We don't want it to cross that position. So can you comment on the velocity at this position? If you know velocity at one place, then you can easily calculate velocity at the other place using one of the three methods that we discussed in the last two classes. Can you tell anything about its velocity when it reaches that position?
The velocity becomes 0.
It stops for a moment, velocity becomes 0 and then it swings back. Okay, so you can take final velocity to be 0. Now you know velocity at one position and you need to find out velocity at another position. What are the different methods we have to do such to solve such problems?
Work energy theorem, sir.
Work energy theorem can be used. What else?
Conservation of mechanical energy.
Conservation of mechanical energy. Okay. If acceleration is constant, you can try to use equations of kinematics. You can use equations of kinematics, but in this case, acceleration won't be constant. We know the object is moving along a curved path. Constant it's moving along a circular path. So constant acceleration is not possible. Fine. Now, which of these two you use is your choice. Work energy theorem has no conditions. Conservation of mechanical energy has a condition. Now, in this case, we have been solving problems like this since like 3 classes. As the bob ascends or maybe even descends, tension is not going to do any work. Gravity is the only force which does work, and gravity is conservative. So mechanical energy is conserved. Work energy theorem can anyway be applied. It's your choice. Okay. So we'll apply mechanical energy conservation. Initial potential energy plus kinetic energy is equal to final potential energy plus kinetic energy. That's all. Rishi, tell me, what kind of potential energy should we consider here? For every conservative force, there is a potential energy associated, and we know two different conservative forces as of now. Then there are two different potential energies also that we have talked about. Which
So
of
we have to take the conservative force as gravitational.
the force acting is the force doing work here is gravity. So that's the conservative force involved in this situation. Then the potential energy you consider will be gravitational potential energy. Okay. Vanilla, tell me the formula for gravitational potential energy.
mgh, sir.
mgh. But we have to assign a reference height first. Now, as I said, when you are applying mechanical energy conservation, it does not matter which level you call as the zero energy level. So let's assume the initial position is the zero gravitational potential energy level, or height is 0. Then the final height will be the length of the string itself. So we'll apply that in the mechanical energy equation. mg into initial height is 0. That's initial potential energy. Kinetic energy is half mu square, should be equal to final potential energy mg. The final height is L. Final kinetic energy, when it reaches there, it can stop. Okay. Now we want the minimum speed with which the string can get to that position. So just after the string gets there, the bob can stop. So that's why the final kinetic energy is 0. Therefore, you get half mu square is equal to mgl. M gets cancelled. U square is 2gl. U is under root 2gl. In fact, we had, okay, let us discuss the result first. If you give a speed of under root 2gl, the bob will just be able to reach the point where it is at the same level as the nail. It won't be able to cross that point. Okay. Hope the solution is clear. We used mechanical energy conservation. We knew the final velocity. Okay. Based on that, we calculated initial velocity. Okay. Now try a slightly different question. Situation is same, but where the bob has to go is slightly different. So you need to calculate the initial speed. Initial means speed at the bottommost position such that the string rotates to this position at least. What position is that? 37 degrees above horizontal. Okay. So length of the string is L itself. Based on the length, by applying little bit of trigonometry, you can calculate this height. And if you can calculate that height, you can tell the total height. to which the bob rises. Okay, I'm giving you some hints to solve it quickly. So if you can calculate that small height, you can tell the total height to which it rises and apply mechanical energy conservation. Try this. Okay. Rishi, tell me, did you calculate that small height above the horizontal position by which it rises? Like it will be in terms of L only. You can visualize this right angle triangle. And if you know one angle and one side in a right angle triangle, you can find out any other side and any other angle. I mean, 90 degrees known anywhere. So anyone, any idea how to calculate that small height first? Let's call it small h.
So H equal to L sine theta.
Okay. Sine 37 degrees is opposite divided by hypotenuse. Hypotenuse is the length of the string. So h becomes L sine 37. Okay, you people seem to be struggling a little bit in calculating these heights and all. So I'll give you some ideas and share some questions with you, practice questions in the next worksheet so that you'll get used to it. So that extra height is L sine 37. Sine 37 is 3 by 5. So this is 3L by 5. Therefore, the total height by which it rises, okay, you can call the total height as the final height h2. Initial height h1 will take as 0. So the final height h2 becomes, the height below is L plus another 3L by 5. L plus 3L by 5 is 8L by 5. That's the final height to which the bob rises. Okay, we found out from which height to which height it goes. Okay. What else do we know about the bob? We want the string to just reach that position. What else do we know about the bob? We need initial velocity. At least tell me this. We need initial velocity. So if you want to use mechanical energy conservation to do that, what other information should you know?
Final velocity. Sir.
Final velocity, correct. Heights we have found out. So the only thing left is final velocity. Vanilla, any idea about the velocity at this position?
0, sir.
Okay, assume velocity there is 0. See, we just want the string to reach that position. So naturally we are like inclined to think that the velocity there becomes 0. Let's assume it becomes 0. Okay, Rishi, tell me the mechanical energy conservation equation now. Like what should we substitute in it? How will you write Ui, Ki, Uf and Kf?
Third U will have to find. So the final U will be 0. The initial
Wait. In the mechanical energy equation, what does U stand for?
Sir, the potential energy.
So talking in terms of potential energy, not the speed. Okay. Initial level, initial height of the bob, we have considered it to be 0. Okay, this height is taken 0, this initial position height. So tell me how much is its initial potential energy? Capital U is potential energy, small u is speed. Okay. So if height is 0, how much is the potential energy? Rishi, what's the formula we use for gravitational potential energy?
mgh2 minus h1, sir.
See, mgh2 minus h1 is the change in potential energy. But at this particular position, how much is the potential energy? How will you specify? What did we do in the last problem?
Sir, we found out that U is equal to root 2 GL.
How much initial potential energy did we take?
mg0, and then
Because that height was taken as zero level. I mean, that level was taken as zero height. So initial potential energy became mg into 0. Now here also we are doing the same thing. So how much is the initial potential energy?
mg0, sir.
Plus kinetic energy formula. Okay, use of what is the formula for kinetic energy?
Sir, it's half mu square.
Initial velocity is u, so it becomes half mu square. Okay. Let Yusuf answer. Yusuf, can you tell the expression for final potential energy now? Potential energy formula is mgh, and you know to what height it is rising. So what is the final potential energy? How much?
So mg brackets L, so L be like 3L by 5.
See, the formula for potential energy is mgh.
Yes,
To
sir.
what height is it rising from the starting point? Starting point is the bottommost position, no? So from this level to what height is it rising?
So 8L by 5.
So the potential energy becomes
mg 8L by 5.
Okay, we write it as 8 mgl by 5. And we are assuming the final speed there is 0, then the final kinetic energy will be 0. And with this, we can calculate u. Okay, but there is a fundamental mistake. There's a conceptual mistake in this solution. We want the string to go to that position at least. We want the string to at least rotate to that angle 37 degrees above the horizontal. But I told you one point in the last class, okay, you may have forgotten that speed becoming 0 anywhere in the upper half of the circle is impossible. Okay, so this is the mistake that we made here. Not mistake, I allowed you to make that mistake. Okay. Remember, speed cannot become 0 anywhere in the upper half. Let us discuss the proof for it first. Now, last class, we derived an expression for v square in terms of theta. What was it? By applying mechanical energy conservation, we did that. And see, I want you all to spare some time, maybe at least 1 hour, to derive these equations on your own. If you know speed at one point, you should be able to tell speed at another point using mechanical energy conservation very comfortably. Okay, so make sure you solve the next worksheet properly. So last class we derived, where is that speed expression? Motion in a vertical circle. Yeah, when the string rotates by some angle theta, whatever it is, the speed expression is this: u square minus 2gl into 1 minus cos theta. Okay. Fine. And we derived an expression for tension also. mu square by L plus 3mg cos theta minus 2mg. Fine. Now we want to prove that velocity cannot become 0 anywhere in the upper half of the circle. Okay. But tell me one thing. Like we have to write some mathematical condition for it. If velocity becomes 0 anywhere in the upper half, means if the bob comes to a rest there, what happens to the string? Or what happens after that? Can any of you tell? In case the velocity there becomes 0, what happens after that? Vanilla, can you imagine and tell?
Sir, it drops, sir.
Okay, good, good. It drops straight down. Okay. Let us visualize that once again. Okay, we'll assume it was moving along the circular path. Starting from here, let's say it has reached somewhere here and the speed there became 0. Let's assume. Then it's a ball at rest. Gravity will be acting on it. Gravity acts in the vertically downward direction. So it will start moving down, and it is attached to a string. String cannot make it go to the right side. Like in that position, like if the string is in this position, I'll write in black. If the string is in this position, it can only pull the bob this way. It cannot push it the other way. Ideal strings cannot push. Okay. And the string has no need to push. The bob has a tendency to fall down. No. See, when will there be tension in an object? We had discussed this when we talked about the basic forces that we come across in daily life. Tension will exist in an object, or tension will get generated in an object when it has a tendency of getting stretched. Okay. Now here, the bob has a tendency to fall straight down. And if it falls straight down, the string actually becomes loose. It doesn't get stretched. It's not having a tendency to get stretched also. So in case velocity becomes 0 anywhere in the upper half, tension should become 0 in the string. String will not be tight anymore. Okay, string will not be pulling anymore. Okay, so if velocity is 0, tension definitely has to be 0. Now let's find out, or let's derive an expression for the angle where tension becomes 0. Okay, we have a formula for tension, right? So T is equal to mu square by L. It depends on the initial speed, plus 3 mg cos theta minus 2 mg. Let's find out where the tension becomes 0. Now for this to be 0, let's keep, where means angle is what we want. Okay, so cos theta is what we are looking for. So we'll keep 3 mg cos theta on one side, send the other terms to the other side. It becomes 2 mg minus mu square by L. Okay. That means cos theta should become 2 mg minus mu square by L whole divided by 3 mg. That becomes 2 by 3 minus m gets cancelled. You will be left with u square by 3gl. So depending on the initial speed u, this is the angle where tension becomes 0. Okay, this is cos of the angle where tension becomes 0. So when cos theta is equal to 2 by 3 minus u square by 3gl, tension becomes 0. Okay. Now what we will do is, we will substitute this value of cos theta in the speed formula and check if speed also becomes 0 at the same point. Because we know if speed becomes 0 anywhere in the upper half, tension has to become 0 at that instant. Okay. So we first found out where tension becomes 0. Now we'll check whether speed becomes 0 there or not. Now the speed formula that we have is, where is it? V square is equal to all this. Actually, if you do all this analysis, it'll be even better, but do it once again. So we get V square is equal to u square minus 2gl plus 2gl cos theta plus 2gl into, in place of cos theta, I'll substitute this now. 2 by 3 minus u square by 3gl. Okay. Now what we are left with is simplification. U square minus 2gl plus 2gl into 2 by 3 is 4gl by 3. Let it be. Minus 2, gl will get cancelled. You will be left with minus 2 by 3 u square. Is that all? Okay. In place of cos theta, we substituted that. Fine, fine. Therefore, we get v square is equal to u square minus 2g, okay, minus 2gl plus 4gl by 3. Okay, 2gl can be written as 6gl by 3. I'll do that. Minus 6 by 3 plus 4 by 3 is minus 2 by 3. Okay, so at the angle where tension becomes 0, we see that the bob still has this much speed. This is interesting. Now you have to consider the result derived for the previous problem. What was the previous problem? how much speed is needed to just reach the horizontal position, and the answer for the previous problem was root 2gl. Okay, these results are very important. If you give a speed of root 2gl here, the string will just be able to become horizontal and then it will come back. It won't cross the horizontal position. Now, if you want the string to cross the horizontal position, u should be more than root 2gl. Okay. Now, if u is more than under root 2gl, then u square will be more than 2gl. Then v square is equal to u square minus 2gl by 3 will definitely be positive. Because u square is 2gl or more than that, then this whole thing will not become 0. It won't become negative. It will be positive. So what have we found? If tension ever becomes 0 in the string, the speed there is non-zero. Now, tension becoming 0 means what? The bob doesn't have a tendency to go out of the circle. If the bob has a tendency to go out like this, okay, just a moment. Suppose the bob has a tendency to move like this, then the string will have to, string's length is limited, no? So the string will pull the bob in and make it move along the circle. Okay, that is when tension will be there in the string. But now at a particular angle, we found out tension becomes 0, if at all. Okay, for this value of cos theta, tension becomes 0. Now tension becoming 0 in the string means the string doesn't have to pull the bob. That means the bob doesn't have a tendency to go in the tangential direction. That means the bob on its own is falling off into the circle like this. But when tension is 0, that means when the bob is falling into the circle, its velocity is not 0. It's just too slow to keep up with the circular path. Okay, so what happens here? Suppose tension has become 0, you will see that the speed is not enough to stay on this circular path. The speed is too less. So as a result, the bob will fall into the circle. It will enter into the circle with some non-zero velocity. So effectively, it's like a projectile now. We had discussed these cases in 2D projectile motion in a plane. When you project an object like this under gravity, it follows a parabolic path. That is what will happen to the bob. Okay, once the speed becomes too less, it will follow a trajectory like this and fall down. Okay, so remember how we proved this. All the derivations are useful now. Last class, we derived an expression for speed as a function of the angle theta. Okay, when the string rotates by an angle, how to find out the speed. We also derived how to find out tension when the string rotates by an angle theta. Now we want to prove that speed cannot become 0 anywhere in the upper half of the circle. As it is, when it is moving along the circle, speed cannot become 0. When it falls off and all, we can't say. Okay. So we first found out, or see, we did some analysis actually. When the bob stops, if speed ever becomes 0 in the upper half of the circle, the bob will have to fall straight down. If the bob falls straight down, we visualized that the string will have to become loose like this. String becoming loose means tension becoming 0. So we proved it in reverse. We first found out where tension becomes 0. And at that particular angle, if you check the speed, you see that the speed cannot be 0. Okay. Therefore, this is the most important point in motion in a vertical circle. If the bob crosses, or if the bob enters into the upper half of the circle, its speed cannot become 0 along the circular path. Okay. You can also say if it becomes too slow, the bob falls into the circle where tension becomes 0. Okay, you can make use of those functions and prove that when tension becomes 0, speed is still greater than 0. That is what we have done. Okay. Now you are asked, like the question that I asked you here was to find out the speed at the bottommost point, which will be able to take it to this angle of 37 degrees. Now we assumed V to be 0 at that position and so tried to solve the problem. That doesn't work. Fine. Now let's think of another idea to solve this problem. How much speed should the bob be given at the bottommost point such that it goes to that height? We have calculated the height already. The final height to which it ascends is 8g. How much was it? 8L by 5. The initial height from which it is starting is 0. So height calculation is done. We want to find out the speed. To apply mechanical energy conservation, we don't know the final velocity at that height. Can any of you come up with some ideas? Think of what all we know in motion in a vertical circle and how any of them can be applied to solve this.
So we can write final velocity in terms of initial velocity.
Okay, okay. See, if you want to apply mechanical energy conservation, yeah, that is a good idea. It can be done. Initial potential energy, we know it is mg into 0, so I'll directly write it as 0. Initial kinetic energy, we don't know. This is something we have to calculate. And this can be calculated if you know final potential energy, okay, that is known to us, and final kinetic energy. So U can be calculated if you know V. So V becomes another variable here, another unknown. We don't know that also. Now what Vanilla is suggesting is we write V in terms of U. Then only U will be the unknown. But there's another thing that you need to do. We have the formula for V square. V square is equal to U square minus 2GL into 1 minus cos theta. Now in place of V square, she is suggesting we substitute this. Okay. But if you substitute that in place of V square, you are bringing theta into the equation. So Vanilla, just one more step and you can solve this. How much is the theta by which the string rotates completely? I mean, I should not say completely. How much is the total theta by which the string rotates?
90 plus 37.
Good, good. Okay. It's very important to remember what we considered as theta in all our derivations. In all our derivations, we took theta with the downward direction. So the total angle by which the string rotates to get to that position is 90 degree plus 37 degrees. Okay. And then you can substitute it and calculate the speed U. That's one way to solve. Let me do this. Listen, I'll give you questions for practice. And see, it's important that you solve problems. Okay. Vanilla is sending solutions to the worksheets, that's fine, but others are not sending me solutions to any worksheet. Make sure you solve problems. At least this case, energy conservation is one of the most fundamental things you'll be using in physics. Okay, so make sure you solve the next assignment and send it to me. Anyway, let's substitute all this now in mechanical energy conservation. So left hand side, we have half mu square left. Right hand side, one term is 8 mgl by 5. The other term is half m v square. Now in place of v square, I'll put all this. U square minus 2gl into 1 minus cos theta is 90 plus 37. Okay. Again, some trigonometry now. Cos theta 90 plus theta. 90 plus theta takes it to the second quadrant. Second quadrant cos is negative. Cos of 90 plus theta, this part, is actually minus sine theta. So minus sine 37 degrees. Okay, it's a trigonometric identity. Cos 90 plus theta is minus sine theta. Now that minus and minus will get cancelled. Sine 37 is how much? 3 by 5. I'll make use of that. So the equation changes to half mu square is equal to 8 mgl by 5 plus half m, okay, u square minus 2gl is there. Let it be. Now you have 1 minus of minus 3 by 5, which is effectively 1 plus 3 by 5. And 1 plus 3 by 5 is 8 by 5. Okay, now you are only left with simplification. Let us multiply the whole equation with 10 so that the denominators will get removed. If you multiply the whole equation with 10, it becomes 10 by 2 is 5. Mu square is equal to 10 by 5 is 2, 2 into 8 is 16 mgl plus, okay, 10 by 2 is 5. I'll keep it as it is. Mu square. Again, 5m into minus 2gl into 8 by 5. There are a lot of chances to make mistakes when calculation is so lengthy. But wait, what are we getting? This is interesting. This part is 16 mgl. This part is also 16 mgl. Minus sign is there, cancels. And you get 5mu square is equal to 5mu square. So the method we tried is not giving us the answer for u. Okay, on the right hand side, we replaced v square with u and theta terms. But if you do that, you are getting u square is equal to u square, as if you didn't know. Okay, so that is not going to help us solve this problem. Okay, that's why I said I will solve this, because I know it won't work. Can any of you come up with any other idea? We want the string to just rotate up to that angle somehow. Okay, see, whenever you are asked questions like this, no, you can think a little bit like what happens after the string gets there. The first idea you all suggested is taking v0. Just when the string gets there, the bob stops. But we proved that speed becoming 0 anywhere in the upper half is not possible. The next idea one of you suggested is let's write v square in terms of u and theta. But that is also not working. So can any of you tell me what happens after the bob gets there? What else happens after the bob gets there?
So like there will be a point at where you'll just stop for like a small, very small amount of time and then start coming down again.
It won't stop at all. We proved that velocity cannot become 0 in the upper half, no? It
Oh,
just
yeah.
becomes too slow. And read this statement. Read the statement carefully. And one of you tell me what happens after the bob becomes too slow to continue along the circle.
Where it falls into the angle and then tension becomes 0.
Yeah. So see, at this moment, when the bob becomes too slow, it was moving in this direction. Okay. But it didn't have sufficient velocity to keep up with the circular path. So what happens with that velocity, or because of that velocity, it follows projectile motion like this. Because once it falls into the circle, tension effect won't be there. String becomes loose, no more tension. Gravity is the only force acting on it. And under the influence of gravity, it'll have to follow a path like this. And that is what it does. So when the bob becomes too slow, it falls off into the circle, means tension becomes 0. We can make use of this also to find out the initial velocity, because tension formula includes initial velocity. Okay, so that's the idea we are going to use. Let me copy this once again. So, okay, the height calculation and all was done. So let me remove that. We don't know the velocity there. But it's not able to move along the circular path anymore. So it falls into the circle. It's falling into the circle means tension becomes 0. So the mathematical condition we are going to now write is when the angle rotated becomes 90 degree plus 37 degrees, tension should become 0. We know angle, we know tension. Only unknown will become speed now. And for this, we won't use mechanical energy conservation. We'll use the formula for tension. Mu square by L plus 3 mg cos theta minus 2 mg. What are the known terms here? We know tension, 0. If it is 0, mass will get cancelled anyway. You don't even have to know. Length is known, gravity is known, theta is known. Calculate the speed u now, all of you. And once again, you can use this identity. Cos of 90 degree plus theta is minus sine theta. Okay, I got one answer as root 19 GL divided by 5. Let's see. What is left is just substitution. So tension becomes 0. 0 is equal to u is unknown. Mass will get cancelled, as I said. You can just remove that term. So u square by L plus 3g cos of 90 plus 37 becomes minus sine 37, that is minus 3 by 5 minus 2g. That's all. Therefore, 0 is equal to u square by L minus 9g by 5 minus 2g can be written as minus 10g by 5. Minus 9 minus 10 is minus 19. This side becomes plus 19. Therefore, you get u square is equal to 19 by 5 GL. Fine. Okay. So remember, the most important thing in motion in a vertical circle is that the object cannot stop anywhere in the upper half of the circle. In the lower half, stopping is possible. How? Let us discuss that also. If it becomes too slow in the lower half, that is not an issue. Let's say it started from here and became too slow when it reached here. Now, even if it becomes too slow, gravity will be acting downwards always. So it has a tendency to pull the bob out of the circle only, not into the circle. Okay, so even if the bob stops anywhere in the lower half, it will have a tendency to fall out, not in. So string will remain tight. But if it becomes too slow in the upper half, then due to gravity, it will have a tendency to fall into the circle. That is when the string tends to become loose. And we proved mathematically that when tension becomes 0, speed will still not be 0. So even as it is falling into the circle in the upper half, speed cannot become 0. Okay, will not be 0. Fine. So with a speed of, okay, like in this problem we found, the speed should be in under root 19 GL by 5. So with a speed of this much, the bob will be able to move along the circle up to this angle. After that, it falls into the circle and comes down like this. Okay. If you give a slightly greater speed, then you can make the bob move along the circle to an even greater angle. And if you give sufficient speed, you can make it go all the way to the top without falling into the circle. Solve that problem now, all of you. In the last problem, you found out the speed at the bottommost position, which will enable the bob to go along the circle up to an angle 37 degrees above horizontal. Now what we want is this. I'll draw the diagram. What we now want is the initial speed that the bob must be given such that it continues along the circle without falling inside, okay, without falling into it. It should continue along the circle till it reaches the top. Solve this problem, all of you. I'll just adjust the diagram. Okay, derive minimum speed at the bottommost point such that the bob reaches the top. Okay, I got the answer from one of you, that's fine. But Yusuf, can you tell how you are going to solve this? The bob should just be able to reach the top. So how will you write a condition for that? Rishi?
Sir, so the height will be 2L,
Okay.
and then
Why did you consider the height? What method do you want to apply?
so that's what I'm wondering, sir, because we have to find like I'm not sure, sir. I'm actually confused as to how to approach this.
What are the different approaches that you can take?
Sir, one is the work energy theorem or the mechanical energy conservation.
See, if you want to use work energy theorem or mechanical energy conservation, you need to know the final velocity. Do you know the final velocity?
No, sir.
Okay, the question that we solved before this also, that was the problem. And how did we find a way to solve the problem? Or how did we solve the problem? Previous question.
Sir, we derived it where v square is equal to u square minus 2gl by 3.
That was before solving the last problem. Okay. V square is u square minus 2gl by 3 was to prove that speed does not become 0 even where tension becomes 0. Okay, we did all that. And we concluded that speed equal to 0, that method is not going to work. Final speed 0 method is not going to work. Okay, that's not valid. Then what was the actual idea we used to solve the problem?
U square minus 2gl 1 minus cos theta.
No, that also did not work. No, when we applied that, we ended up getting this u square is
Then
equal
we
to
took
u
the
square.
tension formula, which we took.
Okay, we want the string to go to a certain position. Once it reaches there, the bob falls into the circle. Means tension becomes 0. Based on that, based on where tension becomes 0, we were able to tell the initial speed. Okay. Now in this problem, in the latest problem, where do we want the bob to go?
Like to the topmost point.
Topmost point. So after going there, see, we want to give the minimum speed which takes it there. So just after reaching there, the tension can become, or tension must become 0. Until then, tension should be non-zero. Is this clear?
Yes, sir.
And yesterday we derived last class that as the bob moves up, tension decreases. So if the tension becomes 0 exactly when it reaches the top, then you can be sure that tension is non-zero everywhere else. As it rises, tension decreases. So at the topmost point, tension is minimum. If the tension there is 0, everywhere else it would be non-zero. Okay. Now, Rishi, tell me, how much is the angle to the topmost position?
180, sir.
So when the angle rotated theta is 180 degrees, tension should become 0. Substitute these numbers in the tension equation and tell me the initial speed. Calculate this quickly, Rishi and Yusuf. Fine. See, the formula for tension as a function of theta and the initial speed is mu square by L plus 3 mg cos theta minus 2 mg. Okay. Now we want the bob to be able to reach the topmost position at least. So just after reaching there, the tension can become 0. So we'll substitute tension as 0.
Sir,
Huh.
I think I got it.
How much?
Sir, it's 5 GL is root 5 GL is equal to U.
Okay, U is under root 5 GL. Correct. Correct. Theta is 180 here. Cos theta becomes minus 1 minus 2 mg. Okay. So on the right hand side, we have a minus 3 mg and a minus 2 mg, which is minus 5 mg. Send it this side. Therefore, mu square by L is equal to 5 mg. Mass gets cancelled. So U square is equal to 5 GL. That means U is under root 5 GL. Okay. So if you give that much speed at the bottommost point, the bob will definitely reach the top without falling into the circle. And if it reaches the top, it will continue moving along the circle down also. Okay. That means it will complete the vertical circle. Fine. Same thing with that Hot Wheels car. We know that we have to give sufficient speed for it to be able to complete the loop without falling down. Okay. So that can be achieved if the car, upon reaching this point, okay, like along this track, it will move down and reach this point. No, just when it reaches here, it should have a speed of root 5g r, where r is the radius of this ring. If it has that much speed, it can complete the circle. Now, this is a real life situation, no? Car moving on a track. So friction will be involved. So you should give a speed slightly more than this in a real life situation. In an ideal case where there is no air resistance, no friction, root 5gr would make it complete the circle. Okay. This root 5gr, that is the speed at the bottommost position, minimum speed at the bottommost position to complete the circle, is called the critical speed. If you give more than that, it's fine. Just a moment. Yeah. So that root 5gl is called the critical speed at the bottommost position. If you give more speed than that also, it's okay. If you give more speed than that, what will happen? Tension will be non-zero even at the top. Okay, that's fine. Tension non-zero means the string is still being stretched, means the bob is staying on the circle without falling inside. If you give a speed less than root 5gl, that is when you have a problem. If you give speed less than root 5gl, tension becomes 0 somewhere before itself. And wherever tension becomes 0, the bob falls into the circle. Okay, so it won't be able to complete the circle. Fine. So whatever we solved till now, we solved with velocity at the bottommost position as the unknown thing. That's what we had to find out. Suppose we give root 5gl, we know it will complete the circle. Now try this problem. And let me remind you the formula we derived for tension, mu square by L plus 3 mg cos theta minus 2 mg, this u is the u at the bottommost position only, not anywhere else. Okay. Now I will change the question. Let's say instead of being sent from the bottommost position, the bob is being given a velocity at this position and released. Okay, when the string is horizontal, we give the bob some velocity in the upward direction. Then it has a tendency to move along that circle, okay? Now you find out how much initial velocity must be given here such that the bob reaches the top. And remember, you may use tension equation, but the u in the tension equation is not this speed. U in the tension equation is the speed at the bottommost position. So you won't get answer from the tension equation now. So think of what to do. The bob should just be able to reach the top. That means we know tension after it reaches the top, tension becomes 0. Think of what all can be done. Okay, Vanilla has given an answer. Vanilla, what is your idea?
Sir, we know that tension equal to 0 and T plus mg equal to mv square by L.
Okay, you are using centripetal force. Good, good. See, we need the speed with which the ball must be thrown in the upward direction such that it can reach the top. Now we know that tension equation that we derived earlier is not applicable here. So we are only left with energy conservation or work energy theorem. And if you want to use energy conservation or work energy theorem to calculate initial speed, you must know the final speed. But how to get the final speed? The hint here is that the object is moving in a circle. And for any object moving in a circle without falling into it or going out of it, centripetal force must be mv square by r. This is what we are going to use now. When the bob is at the top, we need to find out the speed. Okay, this is also one of the ways to find out the speed. Now when it is at the top, tension becomes 0, we know that, but there is still the weight of the bob acting on it, mg. Therefore the centripetal force is mg itself, and that becomes equal to mv square by the radius in which this bob is revolving is L. That's all. So you get v square is equal to gl. That's the velocity at the top when tension there becomes 0. Now you know V, apply energy conservation, you can calculate U. So how do you do that? Initial potential energy plus kinetic energy is equal to final potential energy plus kinetic energy. And it is gravitational potential energy that we are going to consider here. For that, we have to assign the heights. We'll assume initial height is 0. Then the final height, Rishi, how much will it be?
Sir, L, sir.
L. Then tell me the potential energies. How much is initial potential energy if height is 0?
Sir, mg0.
Mg into 0, that is 0. Kinetic energy will be written half mu square, where u is the unknown. Final potential energy,
mgl.
because it is above the initial point by a height L. So it is mgl. Final kinetic energy,
Half mv.
half mv square. V square we derived is gl. Okay. Put all this together and solve for it. You'll get u is under root 3 g L. So from the horizontal position, if you want to make the bob reach the top, you have to give a speed of root 3 GL at that horizontal position. And see, there is another way you could have answered this question by using the result of the previous problem. Understand this approach also. At the bottommost point, okay, let's name these points. Let's call them as A. Bottommost is A. Horizontal, let's call it B. Topmost, let's call it C. To make it go to the top, the minimum speed needed at the bottommost point is root 5 GL. With that, it goes to the top and tension becomes 0. If tension is 0 at the top, no, the speed there will be GL, root GL. From centripetal force equation, we can tell. So for the bottommost point, root 5 GL is the critical velocity. For the topmost point, root GL is the critical velocity. The minimum speed needed to stay on that circle. Okay. If it is root 5 GL at the bottommost point, then the question you were last asked is the velocity at this position, right? Minimum velocity at this position such that it can reach the top. If you are giving the minimum required velocity here, then at every other point also, it will be moving with the just minimum amount of speed needed to get to the top. Okay. You were asked, what is its speed here if it barely manages to get to the top? Then you could have done energy conservation from here to here also. Let's do it. This height will take 0. This height will take L. Then initial potential energy is 0. Initial kinetic energy is half m. U square is 5 GL is equal to final potential energy mgl plus final kinetic energy half mv square. M can be cancelled. 5 GL by 2 on this side is equal to GL plus v square by 2 on that side. So v square by 2 becomes 5 GL by 2 minus GL. That is 3 GL by 2. Cancels, you get v is under root 3 GL. That means if you give the bare minimum speed needed at the bottommost point, then it will reach the point B, the position B, with a speed of root 3 GL. And with that speed, it will be able to reach the top also. Okay, and that's what we have derived in the last problem. So this is also a way to calculate. So basically, if you know the critical velocity at one position, the bottommost position, then based on that, you can tell critical velocity at any other position. That's the idea. Okay, or that's the conclusion from this. Okay.
So can you show the last question once again, the last part?
Yeah, note it down.
Yeah, so done. Thank you.
Okay. So keep this diagram in mind. For motion in a vertical circle, these are the critical velocities at these positions. From bottommost point, it should have root 5 GL. At horizontal position, it should have root 3 GL. At the topmost point also, it should have root GL to stay on that circle. If it doesn't have that speed root GL, no, what happens is it falls off into the circle like this. Fine. Okay. Here, we considered an ideal string and a bob attached to it. Instead of string and a bob, you can be given situations like this also, like that Hot Wheels track and a car. Tell me, in the case of track and car, there's no tension. The car is not connected to a string. What force helps the car take the turn then?
Normal force, sir.
Normal force from the track, correct. So you can see the right side diagram. The car is at a particular position on the track. At that instant, if you imagine this is the center, normal force on the car will be acting this way. Okay, at every instant, there will be normal force. And see, just as tension varies, normal force also varies. Normal force will be highest when the car is at the bottommost position. At other positions, it will be lesser and lesser. At the topmost position, the normal force will be the least, if at all it manages to get there. So in track and object based problems, tension gets replaced by normal force. That's all. The rest of the equations are all the same. Okay, let's consider this situation. Solve a problem based on it. We know that depending on the height from which you release the object, it enters into the loop with different speeds. Small height, it enters with small speed. Greater height, greater speed. Sufficient height, it will enter with sufficient speed to complete the loop. Let's assume the track is frictionless. Ignore air resistance also. Frictionless track. Let's say the radius of the track is r. To find out critical velocities, all you need to know is the radius. Fine. Let's say the radius of the track is r. What you have to find out, I think you are able to visualize, we are looking at this track at an angle actually. That circle doesn't look like a perfect circle. We are looking at it from an angle. So assume this is the horizontal level. Okay, ground level. You should find out from what minimum height the car should be released. From what minimum height the car should be released such that it can complete the loop. So we know that for different heights from where the car is released, it enters into the loop with different speeds. Now the condition is that it has to complete the loop. To complete the loop, you know critical velocities at different points of the loop. Now you have to find out from what height it should be released to attain that critical velocity. If that is done, completing the loop will be done anyway. Okay, think carefully and solve. Okay, listen. What do we know about the requirements to complete that loop? What is needed to complete that loop?
The velocity should be greater than root 5 GL.
Okay, it needs a certain minimum speed to complete the loop. So at the bottommost position, the speed, the velocity, okay, speed only, should be greater than or equal to root 5 GL. So we want the minimum height from which the car is to be released. So it should gain at least the minimum required speed. Means at the bottommost position, it should have, like when it comes to that bottommost position, it should have a speed of root 5 GL. So this is a case where we know the speed of the object at one position and we need to find out the speed of the object at another position. What are the different techniques we can use? Work energy theorem, mechanical energy conservation, maybe equations of kinematics, but mechanical energy conservation is the least. I mean, not least, sorry, easiest. As this car moves down this track, what forces act on it and which forces do, and which of them do work on it? As the car moves down the track, what forces act on it and which forces do work on it? Pawan, can you tell what forces act on it?
Gravitation. Normal force.
Weight and normal force will be acting, correct? Will normal force do any work as the car slides down?
No, sir.
Why?
Sir, displacement in the normal 90 degrees measures.
Normal force acts perpendicular to the track at any position, and the displacement of the car is parallel to the track. Therefore, the dot product between them becomes 0. Normal force does not do any work. Then weight is the only force doing work, which is conservative in nature. Weight is a conservative force. Therefore, just apply mechanical energy conservation between this position A and this position B. Simple. Do this, all of you. You know initial velocity, you know final velocity. You have to calculate the height this time. And in mechanical energy conservation, height also is involved. Apply it and derive the height quickly. Okay, I got the answer from Vanilla. It is 5r by 2, 2.5 times the radius. Okay, simple mechanical energy conservation. Let's assume ground is 0 level. Then this initial height is h. That is what we need to find out. So initial potential energy mgh plus initial kinetic energy 0. The car is being released from rest is equal to final potential energy 0 because finally it's at the bottommost position, which is the ground level, plus final kinetic energy half m v square. V square is 5gl. That's all. You get h is 5l by 2, which in this case becomes 5r by 2. That is 2.5 times the radius. Okay, if you release it from that height, in an ideal case, means in a frictionless case, the car will be able to complete the loop. Okay. Fine, we'll stop it here for now. I'll share the video. I'll send you the notes also. But see, again, Saturday, Sunday, you have 2 days. Of course, tomorrow is festival. That's fine. But at least Sunday, sit for 2 hours and work on this part of the chapter. Okay, this is very, very important. Mechanical energy conservation as a technique is very important. So you should get very comfortable with it. So I'll give you questions based on that angle and height. Calculate the heights, apply mechanical energy conservation, calculate speeds, tensions, critical speeds, all those things. You'll be given problems based on that. Okay, thank you all. We'll continue on Monday.